Okay, let's dive into something that really shifted how we think about training these big language models.
Hmm.
We've all seen models like BERT just, take over the scene for a while. They showed the incredible power of pre-training on just massive amounts of text.
Absolutely. It was a huge leap.
But honestly, keeping up with how these models work, what makes the next one better? It feels like a full-time job sometimes. There's just so much research coming out.
It really is. The pace is just, well, astonishingly fast. And it does create this challenge, right? Understanding the core ideas, the actual innovations that make a difference.
Yeah, getting past the headlines and the jargon.
Exactly. You need to get to the fundamental concepts.
And that's exactly our mission today. We're doing a deep dive into a really significant paper, one called XLNet, Generalized Autoregressive Pre-Training for Language Understanding.
A key one.
Our goal is basically to pull out the most important bits of this research, figure out what makes XLNet tick, how it tried to, build on and improve models like BERT, which we thought were already state-of-the-art, and, crucially, look at the evidence the paper gives for how well it actually worked.
And we're going straight to the source for this. We're looking at the research paper itself, specifically version 1906.08237v2.
Right.
Think of it as us guiding you through the, let's say, the technical terrain of this paper, highlighting the really critical takeaways.
Okay, perfect. So the authors, they start by kind of setting the scene, looking back at the main ways people were doing unsupervised language pre-training before XLNet came along.
Right. They talk about two major strategies. First, you had your traditional autoregressive, or AR, language modeling.
Okay.
These are the models that basically focus on predicting the next word in a sequence, given the previous words, or sometimes predicting a previous word based on later ones.
Like GPT-style models, essentially. Left-to-right prediction.
Yep. Yeah, that's the most common type. They're all about modeling the probability of a sequence of text, but the key thing is they typically operate unidirectionally. So strictly left to right, or maybe strictly right to left.
So, like predicting sad after seeing the cat, but not really using any information that might come after sad when making that prediction.
Precisely. And the paper points out a pretty big limitation there. A lot of the tasks we want these models to do, understanding questions, classifying text, they often need context from both sides of a word simultaneously. Deep bidirectional context.
Makes sense.
And standard AR models just inherently struggle with that.
Okay, which then leads us to the other main approach that became huge, the autoencoding, or AE, pre-training. And BERT is the poster child for that, right? That totally cracked the bidirectional problem.
It did. BERT's big idea was this masked language model objective. You take a sentence, you randomly knock out some words.
Replace them with that special mask token.
Exactly, that mask token. And then you train the model to predict what the original words were, based on all the other words in the sentence both before and after the masked spot.
And because it's predicting based on everything around it, it naturally learns that left and right context that BERT became so famous for. But the XLNet paper argues there are downsides here too.
They point out two main issues. The first one is pretty easy to grasp. It's that mask token itself.
Right.
You train the model, seeing these artificial mask symbols everywhere, but then when you actually use the model for a real task, like analyzing text, those mask tokens are gone. They don't exist in normal language.
Okay. So there's a mismatch between what it learned on and what it sees later. The pre-trained, fine-tuned discrepancy, they call it.
Exactly. It's like, training wheels that suddenly disappear for the race. The model learned with something that's not there in practice.
Yeah, that makes sense. What's the second issue?
The second one is maybe a bit more subtle. It's what they call BERT's independence assumption. So imagine BERT has masked out two words in a sentence, let's say word 1 and word 2. When it tries to predict them, it essentially predicts word 1 based on the surrounding unmasked words, and it predicts word 2 based on the same surrounding unmasked words.
Separately.
Yes, separately. As if knowing the prediction for word 1 gives you no information about what word 2 should be, even if they were originally right next to each other.
Huh. So it assumes the masked words are independent of each other, given the context.
Right. But in real language, words, especially nearby words, are often highly dependent. The paper uses a great example, masking new and York in the phrase, mask is a city.
True.
BERT's objective is effectively trying to figure out P.U. New is a city and P. York is a city independently.
Right.
It totally misses the dependency. The fact that if you know one of the masked words is likely new, the other one is much more likely to be York because New York is a very common phrase.
Ah, I see. So BERT doesn't capture the relationship between the masked tokens themselves in its objective function. It treats them as separate guessing games based only on the unmasked context.
Precisely that, and that limits its ability to model these more complex, sort of higher-order relationships within the text it's trying to reconstruct.
Okay, got it. So we have AR models, good at probability but lack bidirectionality. And AE models, like BERT, great bidirectionality, but they have this mass discrepancy and the independence problem. So how does XLNet try to get the best of both?
This is really the heart of XLNet, permutation language modeling, or PLM. The core idea is quite elegant, actually. They decided to stick with the autoregressive framework, predicting one token at a time based on previous ones, but apply it in a really novel way.
Permutation language modeling. Okay, what does that mean in practice? Are they, like, scrambling the words in the sentence before feeding it in?
No, and that's a crucial point. They're not scrambling the original word order or the positional information. What they permute is the factorization order, the order in which the model is asked to predict the tokens in the sequence.
Okay, the prediction order, not the sentence order. How does that work?
So instead of always predicting left to right, like token 1, then token 2, then token 3, XLNet considers all possible orders.
All possible.
Well, theoretically. For a sequence A, B, C, it might learn from the order BAC one time. Another time it might be CBA or ACB and so on. It maximizes the expected likelihood over samples of these permutations.
Wow. Okay, for a sequence of length t, that's t factorial possible orders. That sounds computationally
Huge. It is huge. They don't literally compute all t factorial permutations, of course. They sample different factorization orders during training.
Okay, sampling makes more sense. But how does predicting things in a random order help the model learn bidirectional context from the original unscrambled sequence? That's the part I'm trying to connect.
Right. Here's the clever part. Think about a specific word in the original sentence. In a standard left-to-right AR model, it's only ever predicted based on words to its left. But in XLNet, because you're sampling all these different prediction orders, that same word will sometimes end up later in the permutation order. When that happens, its prediction can be based on context words that were originally to its right in the sentence.
Ah, okay. Let me see if I get this. If the sentence is, the quick brown fox. In a normal AR, brown is predicted using the quick.
Right.
But in XLNet, maybe one sampled permutation order is the fox quick brown. Now, when predicting brown, the model sees the fox quick. It got to see fox, which was originally on its right.
You got it. Exactly. By training across all these different sampled orders, the model implicitly learns to utilize context from both the left and the right of any given word in its original position.
Okay, that's smart.
And critically, because each prediction within a given permutation is still autoregressive, predicting a token based only on tokens that came before it in that specific permutation order, it keeps the benefits of AR modeling.
So that means no need for the mask token, right? Because it's always predicting a real token based on other real tokens.
Correct. That solves the pre-trained fine-tuned discrepancy issue. No artificial symbols.
And what about the independence assumption that BERT made? Does this permutation approach fix that too?
It does. Because it's an AR formulation within the permutation, it naturally uses the product rule of probability. When it predicts a sequence of tokens that happen to be targets consecutively in the sampled permutation, the prediction for the later token is conditioned on the prediction for the earlier one.
Okay, let's go back to the New York example sentence. New York is a city.
Right. Let's say we sample a permutation order like is, as a city, New York. Now, XLNet first predicts P new is a city. Then, when it predicts York, its context includes not just is a city, but also the new that it just conceptually predicted in this order. So it calculates P, York new, is a city.
Ah, so the probability calculation explicitly includes the dependency between new and York in that step, unlike BERT, which kept them separate.
Exactly. It directly models the dependency between the target tokens based on the sampled order. The paper calls this a denser training signal. It's learning more intricate relationships compared to BERT's masked objective.
That seems like a really significant advantage.
It's a core part of the argument. Now, you mentioned the computational cost earlier. To manage that, they do use an optimization called partial prediction.
Okay.
Similar to how BERT doesn't predict every word, just the masked ones, XLNet typically only predicts, say, the last K tokens in any given sample permutation order. K is a hyperparameter, maybe like 16th or 17th of the sequence length.
So it focuses the prediction effort on a subset, making it feasible.
Right, it makes training practical while still getting the benefits of the permutation idea and the dependency modeling within that predicted subset.
Okay, so the permutation language modeling objective is the big conceptual shift.
Right.
But making it work probably required some changes to the actual transformer architecture, didn't it?
Absolutely. There's a key challenge here. For this permutation prediction task, when you're trying to predict a target token, let's call it X, at a certain position, zits in the original sequence, you need a representation that knows the position zit and has seen the context tokens that come before X in the current permutation order. But crucially, that representation must not know the actual content, the word X itself.
Right, otherwise predicting it is cheating. You can't predict apple if your input representation already contains apple.
Exactly. But then for other purposes, like using this positions as context to predict later tokens in the permutation, or for the final fine-tuning step, you do want the representation as it to include the content of X.
So you need two different things from the representation at the same position. One that hides the content for prediction, and one that includes the content for context. A standard transformer layer just gives you one output representation.
Precisely. It creates a dilemma. A single stream of representations can't satisfy both needs.
So how did they architect a solution for this?
They introduce what they call the two-stream self-attention mechanism. It's quite clever. For each position in the sequence, they maintain two separate hidden state vectors, or streams.
These streams, okay.
Yep. First is the content stream. Think of this like the standard output of a transformer layer. It represents the token and its context, and critically, it does incorporate the actual content of the token at that position. This is the stream that gets used later during fine-tuning.
Okay, that's the normal one. What's the second?
The second is the query stream, G. This one is specifically designed for the permutation prediction task. The query stream representation at position ZILFT only has access to the positional information and the context tokens that came before it in the current permutation. It is explicitly prevented from seeing its own content. This query stream representation is the one used to actually make the prediction to calculate the probability distribution over the vocabulary for what word X should be during pre-training.
Okay, so the query stream is like asking the question. Given the position and the preceding context in this specific shuffled order, but without peeking at the answer, what word goes here?
That's a perfect way to put it. And the way they interact is also key. The query stream at position informs its attention calculation using the content stream representations from the tokens before it in the permutation as its keys and values.
I see. So the query stream gets to learn from the full content-rich representations of the context it's allowed to see.
Exactly. It ensures the query has all the necessary information from the available context to make the best possible prediction without accessing its own content. It's a neat architectural solution.
It really is. And I also recall you mentioning they incorporated ideas from another important model, Transformer XL.
Yes, that's right. Since XLNet is fundamentally built on an autoregressive framework, even though it's this generalized, permuted version, it made a lot of sense to leverage the advancements from Transformer XL, which was a very powerful AR model at the time.
So they pulled in existing state-of-the-art AR techniques. What were the main ones?
Two key techniques stand out. First, relative positional encoding. Instead of giving each word an absolute position number, 1, 2, 3, Transformer XL, and thus XLNet, calculates positional information based on the relative distance between pairs of words.
How far apart they are.
Yeah. The paper suggests this relative approach helps the model generalize better to sequences of different lengths or structures.
Okay, that makes sense.
Yeah.
And the second technique?
The second, and perhaps even more impactful one, is the segment recurrence mechanism, often just called memory.
Memory. How does that work?
This is really important for handling long texts. Standard transformers have a fixed input window size. Transformer XL introduced a way for the model to cache the hidden states computed for a previous segment of text and reuse them as context when processing the next segment.
So it can kind of remember what happened in the text that came before the current window.
Exactly. It allows the model to maintain context over much longer distances than the fixed input length would normally allow. This is super valuable for tasks where the answer might depend on information presented much earlier in a document.
Right, like long articles or book chapters. That seems like a huge advantage for reading comprehension.
Absolutely. And the paper explicitly points this out. The performance gains on tasks like squad and race are partly attributed to this memory mechanism.
Okay. And how did they handle inputs with multiple parts, like a question in a passage? BERT used segment embeddings for that.
They use a similar overall structure like CLS, segment A, SEB, segment B, a SEP. But instead of absolute segment IDs like segment 0 and segment 1, they also use relative segment encodings.
Relative again?
Yep, the model basically just learns whether two tokens belong to the same segment or different segments. It doesn't care if it's segment A or B, absolutely, just about the relationship.
Which, like the relative positions, maybe makes it more flexible. The paper mentions this could potentially allow fine-tuning on tasks with, say, 3 or more segments more easily than BERT's fixed A-B approach.
That's the idea. And interestingly, they did ablation studies tests where they removed specific components and found that the next sentence prediction, NSP objective, which BERT used to learn relationships between sentences, didn't actually provide a consistent benefit for their XLNet large model.
So they just dropped it.
For the large model, yes. They found the permutation objective was powerful enough on its own.
Okay, so we have this innovative permutation objective, the clever two-stream attention to make it work, plus the power-ups from Transformer XL like relative encoding and memory. That's the theory. How did it actually perform? What did the results in the paper show?
Well, the empirical results they presented were pretty strong, quite convincing, actually. First, they did a direct comparison with BERT large, trying to keep the training data and hyperparameters as comparable as possible. That's in Table 1 of the paper. Even in that head-to-head, XLNet significantly outperformed BERT on a whole range of tasks, things like question answering on Squad, various GLUE benchmark tasks covering inference and classification, text classification, pretty much across the board.
So even without just throwing more data at it,
Yeah.
the core approach seemed better.
That's what those initial results suggested. And then, of course, they did scale it up. They trained XLNet large on much more data.
Right.
And in those scaled-up comparisons, shown in tables 2 through 5, they reported that XLNet generally outperformed both BERT and also Roberta, another strong model that came out around that time across that wide spectrum of benchmarks.
You mentioned the memory mechanism helping with long texts. Did the results bear that out specifically?
Yes, the paper highlights that. They note the performance gains were often particularly large on tasks requiring understanding of longer contexts. Reading comprehension like Squad, and especially race, showed substantial improvements.
Makes sense. The memory is paying off there.
They directly attribute a good chunk of that gain to the recurrence mechanism from Transformer XL. But it wasn't just long context tasks. Even on large-scale classification datasets like Yelp or Amazon reviews, they still showed significant gain over previous models.
Impressive. What about their ablation study? You mentioned they tested removing parts. What did that show was most critical? That's usually really revealing.
It is. Table 6 has those results. It clearly showed that both the permutation language modeling objective and the Transformer XL backbone were essential. Removing either one caused a big drop in performance compared to the full XLNet model, bringing it much closer to a BERT baseline.
So it really was a combination deal. The new objective needed the better architecture, and the architecture showed its full potential with the new objective.
Exactly. It wasn't just one trick. The ablation also confirmed the specific benefit of the memory mechanism, especially, as we discussed, for tasks like race with very long inputs. Taking memory away hurt performance there noticeably.
Any other key takeaways from the ablation?
They also showed that other implementation details mattered, things like predicting spans of tokens instead of individual ones sometimes, and using a specific bidirectional data input pipeline during training. These also contributed positively, and, as we mentioned, it confirmed the next sentence prediction objective wasn't helpful in their setup.
Okay. And they also looked qualitatively at how the model was paying attention.
Yeah, briefly in the appendix. They showed some examples where XLNet's attention patterns looked different from typical transformers. They found patterns like self-exclusion, where a position attends strongly to everything except itself, or relative stride, where it focuses on tokens a certain fixed distance away.
Different ways of looking at the context.
Possibly enabled by the relative attention mechanism, they suggest these unique learned patterns might be part of why it performs so well, allowing it to capture different kinds of relationships in the text.
Fascinating stuff. Okay, so let's try to wrap this up. XLNet emerges as this uh, generalized autoregressive method.
Right, using permutation language modeling to try and get the best aspects of both the AR world and the AE world.
Avoiding the pitfalls of both, like the mask token and the independence assumption of BERT, while gaining that crucial bidirectional context.
hmm And its key technical contributions were really that PLM objective itself, the necessary two-stream attention architecture to make PLM feasible within a transformer, and then smartly integrating the powerful ideas from Transformer XL, especially relative encodings and segment recurrence memory.
And all backed up by pretty compelling empirical results showing state-of-the-art performance across a wide variety of NLU tasks at the time.
Definitely. It set a new benchmark for a period.
So, thinking about the bigger picture impact, what did the authors see as the main message from XLNet for the whole field of language research?
Well, they make a point about bridging a gap. For a while, there was maybe a disconnect between pure language modeling research focused on accurately modeling the probability of text, like density estimation, and the pre-training work focused purely on downstream task performance.
Right, two different goals almost.
XLNet, they argued, showed that improving the fundamental language modeling objective itself through PLM could directly lead to major improvements on practical downstream tasks. It validated the idea that pushing the boundaries of how well we can model language probabilistically is a really fruitful path for improving AI's language understanding capabilities overall.
That's a great point. It shows that the fundamental science and the practical application can really drive each other forward.
Precisely.
So, as we finish up, here's a thought for you, our listener, to maybe mull over. Consider what it really means for a machine to learn relationships between words based on potentially any order, not just the fixed left to right we're used to. Combine that with the ability to effectively remember context over very long stretches of text. How might this deeper grasp of context and relationships, unbound by simple linearity or a short memory, open doors to new kinds of applications? What complex texts or long-form information could suddenly become truly understandable and usable by machines in ways we haven't even fully imagined yet?